So we're gonna talk about A/B testing, which I mean, I don't know. A/B testing always kind of cracks me up a little bit because it just seems like such a bigger deal than really what it is. It's really hypothesis testing. It's just a very specific way of doing hypothesis testing. But for the most part, if you go into a business or anything, they might not know what hypothesis tests are. But if you say an A/B test, almost every business will immediately go, oh yes, an A/B test. And in fact, if you're in an interview and whatnot, they're probably going to ask you, do you know what A/B testing is, or questions about A/B tests and stuff like that. So just kind of be aware. It's like just more terminology. It shouldn't be too scary. Nothing in life is really that scary. Just gotta go with it, right? So I'm actually going to just to kind of get you guys a feel for, where did I find it? Aha, here it is. Okay. So I'm going to go ahead and share my screen in 1 second. Man, all my windows popped up and I'm like, which window is it? I think it's this one. Yeah, that looks like a window. Oh, good. And Zoom didn't put my windows all too crazy today. So I found, like, literally I just searched, I'm like, this might be a good thing to kind of check out is interview questions for A/B testing, right? So like literally I just searched, A/B testing, like I think I literally put in what is A/B testing just to kind of see what pops up. That's always a good place to kind of start just to see what's out there. And a couple pages kind of came up. This one was about a bunch of A/B test questions and stuff like that. So what is a confidence interval? What do you think about A/B testing? Or when should you perform A/B testing? So you can see here most of this stuff is you'll read it and you're like, oh yeah, I think I kind of understand that stuff. And again, because it's really just hypothesis testing. And almost every hypothesis test basically boils down to, no matter if you're doing a t-test, f-test, ANOVA is kind of related to an f-test, but whatever you do, you essentially come down to getting something equivalent to a p-value. So you might have a t-statistic, you convert into your p-value, and then you have your critical value, which is your alpha, and you compare the two and you say, all right, my alpha value says, how weird am I allowed to accept things? How weird do things have to get until I say, okay, I can reject the null hypothesis? And the p-value is, how weird is my actual data? Is my data really weird? And the smaller your p-value is, the weirder your data is. Basically, there's a smaller probability of it being explained by the null hypothesis, which again, the null hypothesis, null meaning nothing, it means no change. You can think of it as your control sometimes if you're more in the science kind of realm. But for the most part, basically the no change part, the thing that you're comparing, okay? So anyway, I thought this was kind of a cool thing. Literally, I could share you the link, but it doesn't really matter because honestly, you could just type in, what is A/B testing? And it probably would pop up 1,000 different things. You might even have to go more narrow because there's so many things, okay? So yeah, we'll kind of talk about that then. So real quick before I kind of move on to everything going forward, who has at least started section 22? Just give me a thumbs up, a shy little thumbs up if you have. Okay, so I see a thumbs. That's right, Bardo, you told me just starting it. And that's fine. So yeah, if you're just starting it or haven't started it yet, just know it's similar to section 21, which is hypothesis testing. It's more like scenarios than anything. That kind of gives you some help. But I wanted to give you guys a warning because I might talk about the solutions a little bit for that part. I might reference it a little bit. So if you want to, spoiler alert, I guess, for solutions or whatnot, I don't think it'll be a big issue or anything like that. But just moving forward. Okay, so A/B tests, basically you can kind of break it down into multiple parts. You can I was trying to see what other people would say A/B testing is. But I really break it down into basically 2 parts. It's or 3 parts, I guess, in here is what are you going to test? Okay. Are you going to roll it out? So are you going to actually do the testing? Then you need to determine how many subjects you need. And then the 3rd part is if you already have the data, which would be after you perform the experiment, right? What kind of tests do you actually need to do? What kind of hypothesis tests? And that's pretty much it. In my opinion, A/B testing makes it sound a lot scarier than it really is. So kind of just going through a little bit quick steps, and this should hopefully be review if you've gone through section 22, or it might be new to you. Basically, what are you going to test? What metrics are you going to use? So those are really important, is that you can do hypothesis test statistics on whatever you want. Is that going to mean it's meaningful? Not always, right? You have to figure out what metric actually is something meaningful. And this is where this is probably the biggest and most difficult part. of the statistics part. And like, this is where I like to say is like the statistics itself is not usually too hard. It's usually interpreting and understanding what thing to do. So for example, we're going to go through an example, which is like the classic, you know, modern day example. It's like, oh, a company has a website and they're making changes to their website and they want to know, what's it called? Like, you know, will this make a difference? You know? And so how do you measure, will it make a difference? How do you measure your website's doing quote unquote better? One classic one is like click-through rate. So how many times do people look at it and versus how many times people actually click on it? So like, you know, you might have a certain percentage of goal or, you know, want to see if you do better and stuff like that. A 1% change might mean nothing to some companies, and a 1% change, depending on the company, might mean a huge amount of money for them. So it's all in context of like what it is. Click-through rate might not be the best metric. Maybe there's other things that they can do too. Maybe view time, for example. If anyone follows, I know YouTube's a really interesting one for me because they have a lot of metrics that they can use. And you can see, because YouTube's so huge, whenever they make a change to, at least, you know, they never say exactly what they're changing, but if they make a change to one of their metrics and like how they, you know, decide on what videos to suggest to other people, people see this huge change. So if you make a change in not how many times a video is watched, but instead of how long a video is watched, that could be a different thing. So like if you make very, like if you guys remember not too long ago, like I guess it's kind of a while ago, like 5-8 years ago, YouTube videos for the most part were relatively short. Like they're like 3 minutes long at the longest, you know, but nothing like 10, 15, 20 minutes or anything like that. That was like ridiculous. Nowadays, I mean, I don't know if anyone watches YouTube really, but if you go through it now, a lot of the videos suggested on there are usually longer content, and a lot of the videos now are, you know, 10, 15, 20 minutes. And there might be a few reasons why and stuff like that, but it all comes down to the way how YouTube did their metrics, which encourage people to do certain things for their own videos and stuff like that. And basically, this is where all these things happen. So you're deciding which metric to do is a huge important part, and it all depends on the context of what you're trying to achieve. Okay. But once you know your metrics, you just state your hypothesis, your alternative, or your null hypothesis, and your alternative, H0, H1. Sometimes you see H0 and HA as alternative hypothesis. Depends on, you know, what sector of people you're talking to, but for the most part, is H0 is your null hypothesis, and your H1, just to clarify. In A/B testing, does anyone take a guess what usually our alternative hypothesis is? Like, let me think here. What's that?
That B is significantly different than A.
Yeah, so B, so there's a few options, right? B is significantly different. It could be that B is better, right? Better, whatever, greater than. And it turns out it's usually better. Sometimes there can be difference, but usually businesses are saying, oh, we have this thing and we make this change. Is it better? They don't care if it's like the same or worse. They're just like, I just care if it's better. Sometimes it's not true, but you know, for the most part, you're probably testing about, is it greater than? Are you getting a better click-through rate? Are you getting a longer view, view time? Are you getting, you know, more sales, you know, whatever it is, more profit, whatever the metric is. So for the most part, they're kind of relatively simple, but it's important to state your hypothesis so you know what you're actually testing against, right? So then this goes up to the next stop. Like, okay, like we're gonna roll it out. So we haven't done the experiment yet, you know, we need to determine how many subjects we need. Basically, you want to do this because you want to minimize the effect to a business. So if you imagine all of a sudden you change the button from like, I'm going to use YouTube. If I change YouTube's color scheme to blue and I change that for everyone and they find out blue for whatever reason, people psychologically just like, oh, I don't really want to watch these videos anymore. So they stop using YouTube. That just made YouTube out of business, right? Or like lost a huge amount of money. So you want to minimize the effect. You want enough people to measure a change, but also not so many people that you're going to drastically affect the business. So this is why we want to figure out what the sample size is usually. And then we use power and required significance. And this is where this is kind of like more or less subjective. It's saying what kind of power are we willing to accept and what kind of significance are we willing to accept. And those are represented by beta for power and alpha for significance. And again, alpha, like I'd say, is like how different does something have to be? Like how weird does it have to be for us to accept it? Like, is a difference, is a slut, like, I'm trying to think of a good example of this, but basically it's just like how certain do we have to be of this difference? And then our power, of course, is really saying how many false positives are you allowed to accept. And usually beta is around, oh shoot, I'm messing this up. Usually we say statistical power is about 80%, 0.8, beta meaning 0.2, so it's the inverse of each other, one minus the other. And then alpha is usually 0.05. That's kind of, it's kind of funny. We kind of all accepted like 0.05 as the critical value. It's not really like a thing that you necessarily have to say it's always 0.05. It could be whatever you want. Usually though, we're about that. You might want to go lower if you want more significance and stuff, but it all depends on whatever field you're looking at. Okay. Any questions on those, guys? This is hopefully reviewed from like our study group before. Cool. All right. And so then once you have the data, basically you just have to figure out what test it is, determine what kind of test you have to do. In all likelihood, you'll probably do a Welch's t-test to make a comparison. Welch's t-test just basically, it's a t-test means that you have degrees of freedom, but Welch's mean that you don't have to rely on the fact that your samples that you're comparing the two are the same, and their variances don't have to be the same either. And then that's here, identify any conflicting factors. So that's an important one, is that note that just because you get a significant value doesn't necessarily mean it's causing that thing. It could also be related values. We saw, like, for example, like I think it was Nicolas Cage and number of drownings or something like that in the movies with that comparison. You have to be careful about, like, you know, like, well, is there some conflicting factor? For example, maybe it's just like summer or whatever. Like we talked about, like ice cream and drownings and things like that. Okay, cool. And going back to just real quick conflicting factors, one quick thing about A/B tests, because you are making a change, be aware of things like change aversion and, oh, I'm forgetting the word I had before. When basically, like when it's new things, people are like, ooh, cool, this is new and exciting. And so they're more likely to use this thing. So note that you might have to give it more time to make sure those kind of factors kind of roll out a little bit. This is where, like, you know, this is where huge amounts of people would be really useful. Okay. Cool. Any questions about this kind of A/B test in general? Or anything I talked about at least so far? Okay. All right. And then I know people have definitely specific questions about A/B testing. Is there any specific questions that you guys were just going to ask now before I kind of dive into an example? Yeah. I think I see Nicole maybe say something.
Yes. Yeah. I just remembered in this section about like the different like error type 1, error type 2. I think it was mentioning the fact that you might want to like set your p-value depending on which error is more would have a like more negative impact. Is this something that we should think about as well, and maybe set the values differently?
Yeah, and that's directly your alpha value and your beta value are basically, and beta meaning like power, are related to your false positives and your false negatives for alpha. And so that's really what you're testing between the two, is how many false positives you're allowed. So if you are allowing yourself more false positives, you're increasing, let me make sure I got this, you're increasing beta, lowering your statistical power. And then alpha basically is saying how many false negatives are you saying, how much do you have to like accept to be weird enough to basically accept that through. And those are the connections between those two, basically alpha and beta. And usually we don't say beta, usually only like nerds talk about beta. But like I'm talking about like people who are like really into statistics. Usually you're talking about statistical power itself. So, okay.
Okay.
All right. Cool. So cool. So let's kind of give a little example. I kind of was trying to figure out like what was the best thing to do. At first I was just going to do like a lab for you guys. But I kind of feel like, you know what, let's mix it up a little bit. So I went ahead and went to Kaggle here, and I just looked up the first thing. I was like, oh, let's try a click-through rate. And I just basically found a competition that already exists. This is from like 5 years ago. So like this competition's done. You can't win any money. Oh, that's too bad. But you can, you know, these guys won some money. So hey, good for them. But anyway, this is a data set from this company, Avizu. I don't know. So basically they're trying to predict whether or not their mobile ads will be clicked, right? And so they have a bunch of data basically, and they say, all right, what our click-through rate, and they wanted to make a prediction on this. So this would be more machine learning, but we're going to use this more hypothesis testing to see if it's significant or not. So we're just saying, just getting some data. It's kind of interesting. They provided 11 days worth of this data. You can kind of look at this real quick. And there's some, they talk about strategies, stuff like this, and you can check out the data. And this is where Kaggle has a lot of, interesting data. You don't have to use competition, you can use data sets. I just grabbed this one because it's already existed. So it's about 11 days. And you can see here, these are different fields. There's an ID, a click, so 0, 1 for non-click, click. So this is our like a data dictionary, right? Hour, basically when it was clicked on. So that would be interesting, the prediction saying, oh, maybe people click it more on late at night because they're like, super tired or whatever. And you can see like banner position, site ID. There's a few other things. I think I looked at device ID or device type or connection type. So those could be like, is it using an iPhone, an Android, or some kind of variant of Android, whatever they're kind of modeling over. Are they using Chrome? Are they using Safari on their mobile? Those kind of things. And then they also have, you'll see this sometimes with data sets, anonymized categorical variable. So we don't know what that is, but there's some category that might be useful to this. And so this might be anonymized for our privacy to make sure that maybe there's some information about a person. We don't want to like leak this out, and they're doing hopefully the ethical thing in the sense that they're not releasing this information by accident and people can reverse engineer. So usually Kaggle has like, a sample submission, and then usually they have some like tests and train data. So if you download this, I think it's about a gigabyte compressed, but when you uncompress it, it's like, I think the training size is 6 gigabytes. So it's a pretty big set of, like, it's a CSV, it's a huge CSV. So I'm just gonna show you guys what this looks like. And I'm gonna pretend, like, oh, we already downloaded it and I uncompressed it for you guys to make it nice and easy. So this is uncompressed, oh yeah, 6.3 gigabytes. So you can see, yeah, it's pretty decent size. And so one thing you should know, and we'll talk about this more when we get into more machine learning and modeling, Pandas is a really great way to test things out. You have to be careful because Pandas also like loads it directly into memory. So if you have like, 120 gigabytes of information and you try to load into Pandas, Pandas will crash. Your computer will basically stop because you can't load it all in there. So there's a few things you can do. One is basically using other things like PySpark, which we'll kind of talk about a little bit more. And there's other ways we can like load it in chunks essentially. So we're going to try some of those things. But I kind of show you right now, it's like, well, I kind of don't want to do this 6 gigabytes. So one thing I could do is I'm going to go ahead and make a new terminal directly in here. And let's see here. Forget the path to be here. So Flatiron, resources, oops, it's not resources, it's study groups, code alongs, and then what do we got? I'm just reading the top right here, A/B tests. So this is just getting into the path. So we can see here, we got data, those steps I just showed you. So let's go into the data. And you can see there's the Abazu. I don't know, I don't like pronouncing things, okay. And you can see here's our training data. And so again, I don't want to, like, one thing I could do is like, I could split this training data into something nice and small. So one thing I could do if I'm in the terminal, and this might happen if you're like logging in from like a cloud server and stuff like that. So this is something we can talk about maybe in the future. But if you're doing this, you might only have access to this. So you might do a head and you do head like train. So this is basically kind of like, head for a data frame. And so basically you'll read the first, I think it's the first 10 lines. First 5 lines. So you can see here, basically this is the first line here with all the columns. And then this is the second line right here, which is basically all the information. And it shows out 10 different lines. So it's like, okay, cool. Like I can kind of see what that is. There'd be a lot of data in here. So what I might do, I can also do like specify the number of lines by saying, okay, let me print out the first 3 lines. Okay, and you can see here, it bleeds over on the edge. So you can see this is the first line. The second line, this is the third line. It's like, okay, that's kind of cool. So let's say we just want the first like something small, it's like 500 lines, right? And then I can actually, instead of it just printing out, I can actually save this. This is fancy Unix right here. So you make sure if you're on Windows, you have to use git bash. But in Unix, you can basically say, okay, head-n 500, so 500 lines of this document called train, which is a CSV. There's no extension, but it's going to figure it out. And this arrow right here means it's going to export, it's going to dump whatever it's going to print out into whatever I give it. In this case, I'm going to give it a file name. So I'm going to call it train short, I'll call it 500. And let's just call it, oops, did I press enter? Oh no. Okay, and I'll call it this part. So what's going to happen, it's going to basically take whatever it's going to read out here and dump it into this file. This is a really quick way to like get a short amount of information. So you can see here, if I go to data, you can hopefully see there's that short 500, and you can see much smaller than 6 gigabytes, pretty easy. So this might be something you want to do, like just to get a chunk of it. I could also done like, something larger. I could have done like, let's say 50,000, which is probably closer to like what you would want to look at. So maybe like 50K. And now I have another one, and you can see it's relatively small as well, 8 gigabytes or 8 megabytes, nothing too big. So that's one way we could do this. Another way we could do this, which I think I kind of prefer because it's directly in Pandas, is I'm gonna go ahead and make a new notebook. So I'm kind of starting to like, this is a little different from my normal, like I think you guys probably see. I'm just kind of typing away. So I'm going to import pandas as PD, and then I'll go ahead and import NumPy as well, because I just like NumPy. So always good to have it in my back. So I'm just going to just write it here, like, read in part of the data. And let's see here. So I'm going to do pd.read CSV, right? Okay. And this is kind of fun. So I can just start typing, like I have to type the name, and remember I have to do the path, right? So I have to go to data and then this guy and then inside. So one thing I could do, I could just do data. I can tab that. So it's pretty smart. So, oh, I know what you're talking about. And then if I do tab again, unfortunately, you can see there's some extra stuff in here. It's like, oh, that's kind of long, right? So what I can do is I can make it a little bit limited. Oh, let me start typing oh, there it is, APSU. So that's a quick way to do it. And then I don't want the whole training data. Well, I could, for example, just do the short list like this, 50K, but I'm gonna show you guys something a little more fancier. I'm gonna do the whole thing. And normally I'd have to read that whole thing in there and like, oh, that's not good, right? So what's cool is that there's a bunch of functions built into, or not functions, parameters built into the function read CSV. So I just did a shift tab, right? This is just the documentation. I'm pulling this up here, and you can see here's the whole doc string. So if I go search pandas read CSV, this would come up as well. And I'm just going to show you, there's a little term here that you see there's a bunch of things that we can do in here, and I'm just ignoring a bunch of them. But we can do n rows, and n rows are basically number of rows of files to read. So it's useful for reading pieces of large files. Hey, okay, that's what we want. So we can go ahead and say, all right, how many rows do we want? And we'll start off with something relatively small. So like, I don't know, like 1,000. That's pretty small. Okay, so we got this part in here. We could do other things in here. For example, NA values. We could do things like, change them over or whatever, but we're just going to keep it the way it is, right? Just to see what happens. And we'll go ahead and save this as our df because I don't know. I don't like calling it this. I'll df raw. I don't know. I don't like when variables are just like a single letter. All right. So we can see here if we do df raw now dot head. Away. There we go. And I realized too, this is kind of small. Let me go ahead and expand this out. Yeah. And I'm going to get rid of you. I don't need you. Okay. So you can see here, we just did a quick head, and we can see here, here's the ID, click, some other columns and stuff here, device type, connection type, and some unnamed columns and stuff like this. So, if I wanted to show that, I can also do df columns to see, what columns are available in here. Oops, I forgot. I didn't call it df. I called it something nice, raw. Okay. What was it? Columns. You can see here there's different columns, and you can see, okay, there's some missing ones. For example, after app domain, there's also app category, device ID, device IP, and so on, right? So this might be some interesting thing to do. Notice the first thing I should say is like, oh, ID. Like ID probably means, something specific, specific to that user. So we can look here, ID, usually add identifier. It's like, oh, okay, well, that's good to know. I would have thought at first as the person who clicked it kind of thing, but it looks like it's the actual like add identifier. So this looks like it might not actually have the person's actual like who it is. So that's something important to note. So this data might include the same person over and over again, maybe for different ads. And when I say different ads, I'm thinking like it's probably, even if it's the same ad every time, it might have a different identifier. So that's something you might have to look closer into and all that stuff. So my guess is that there's going to be a unique identifier for every single ad that we look at. And just to check this out, here we are. I'm going to close this guy since we don't need him. So just to kind of check this out, so, okay, let me just do df raw, and what are we doing? That ID, right? So let's do, let's just do count. Oh, there we go. So I need to do value counts, I just realized. All right, let's see. Let's do ID that's and unique, right? Okay, and you can see, oh, cool. So there's 1,000. So we have 1,000 columns or 1,000 rows. So there's 1,000 unique ID, right? Compared to if I do, like, for example, click can only be 0, 1. There should only be 2 of them, right? So that makes sense. Okay, cool. Does everyone follow me so far? Cool. All right, so cool. Like, we kind of explored a little bit. So here's a question. What do you guys want to look at? So what things might you want to see if there's a difference between, we'll make a control and we'll make like a experiment group. What of these columns sound interesting to you guys to maybe test against? And I'll go ahead and do it like this. It's a little easier to read.
Maybe the banner position? Banner
position, okay. So yeah, and let's just double check what banner position is. Oh, doesn't really say us. Well, we can probably guess it's some position of the banner, right? I saw at first there's a 0 and 1 here, so let's see what that looks like. And remember, we only have the first 1,000, so there could be a lot more values, but we're just kind of playing around a little bit. So let's go ahead and do the banner position. Oops. And I'm going to do a different style just to show you guys a different way of doing it, right? So banner position, we'll do, let's do value counts. You can see, okay, 0 and 1. So good to know. So that actually makes it really easy for us. It's like binary. It's going to be control and experiment. So we kind of take this. And notice too that they are different numbers, right? 815 and 185. So most of them have a banner position of 0, whatever that means. Okay. Also note that we didn't really shuffle this, so just know if the data set is specifically like ordered by banner position, we might be getting something like that. So if we really cared, we might want to do more or shuffle our part in there. I think there's even a shuffle if you were to kind of go into read CSV. I think there's even a shuffle based in here. Maybe. You see how there's so much stuff? Yeah, I'm not going to go look for it. Maybe there's something. Okay, so but basically, we have the first 1,000. So, okay, we'll just play with this. So cool. Banner position. Is there anything else that maybe we can check out later?
Maybe like site category. I would assume that's like what type of website that is on, maybe.
Okay, and what's that, site category? Cool. Let's check out site category. And so as I check out, I'm making notes to myself, right? Banner position. And so this is how you would realistically like go through your data set and say, all right, what's interesting? What's going to be something, you know, I should look into? And I'm going to go ahead and make this. Let's check out, what's it called? Oh, I saved it. All right. Thank you. Copy and paste. All right. So we do df raw, and then we'll check out site category, and then we'll do .value counts. Oops. So we'll see what this is, looks like. Oops, did I do this wrong? Oh, value counts. Stinking S. Okay, oh good. I was gonna say, oh no, it's gonna be a huge list, but you can see there's not too many, right? So whatever this category is, tag category 28905 EBD, yeah, that category. You can see that we can see all these different distributions. There are some other ones on the end here, which maybe from the fact that we only are pulling 1,000. So we might not want to look at these specifically, at least for this analysis. We probably would want to skip this one too. These ones are probably closer. The closer the number of like sample size, probably the better. But you know, we don't necessarily have to have it equal. Okay. So cool. So I'm going to go ahead and we'll start with banner position because that seems like a pretty, you know, straightforward binary yes or no kind of deal, right? So, and I realize I have some notes here for myself to make sure I follow along my own kind of deal. Okay, so we went ahead and read it through. We saw the different value counts and everything like that. So we want to make a control and experiment, right? So let's go ahead and define a control and experiment. So in this case, there's not really clear what the control is versus the experiment is. Like, right, we're just kind of making something up. So we might also call it like A, B or whatever. But you know, come from a science background, I always think control experiment. So I'm going to stick with that. So I'm going to go ahead and say define, oops, I realized that's not code. So let's go define control and experiment groups, right? And then once we find those experiment groups, right, we want to determine the hypothesis, right? So let's just say, like, you know, determine, let's say state hypothesis, right? So this is just for us tracking, making sure what we care about and everything like that, okay? So I really could probably just state the hypothesis right now. So what do we want to say, guys? We say, I'm just going to say banner position 0 is control. That seems like a good one. Banner position 0 seems like control, right? So I'll go ahead and write my hypothesis, right? So let's go our null hypothesis. So what would be our null in this case? And then later our alternative.
Like no change.
So what? Let's formalize that, right? When we say, let's see, what are we look?
So is it number of clicks, right?
Mm-hmm.
So ads on a banner get the same number of clicks as ads that are not on the banner.
Right. So let's say average clicks, right? Let's see. Do we care if it's greater than, equal, or I guess no? They are equal, right? Or is that something different?
Or yeah, or less than or equal to. If we want to test that it's greater.
Yeah, good. So we want to actually see if it's different, right? We want to see, or not different, if it's actually better, less than or equal to, right? So we do average clicks. We'll just call it position 1. So this is kind of just, it's kind of messy. You could come back to this and kind of fix it up later and everything like that. But the point is, like, you know, we want to state what we're actually looking for. And so what our alternative would be is opposite this, right? So clicks cost 0, and what's the opposite of this?
Greater than.
Right. Yeah, I'm really walking through this, right? So, all right, so we got our hypothesis, right? This is what we want to check out. So I'll just go to put a little thing right here is, okay, so that's our hypothesis, all right? And then we actually want to go ahead and make our control and experiment, right? So let's go define our control and experiment. We'll say control is, like we said, position 0, right? So control is equal to df raw. We want to get where the banner position is equal to 0. So anyone got an idea how we would write this out? There's a few ways we could.
You're grabbing the column that's banner position equal to 0?
Yeah, right. So we want the banner position that's equal to 0. So there's going to be something like banner pots is equal to 0, like that, right? So how would we write this out, you think? So we could get, from that data frame, we get just that.
You could either use the dot or the square brackets.
Okay, so square like that.
Yeah, and then parentheses.
Yeah, like that.
Mm-hmm.
Okay, so let's just see if that works, right? And so something didn't quite work out here. So it says we have a key error. So what might we have messed up here? You got an idea?
We have to use like the iLoc or location.
We could do some stuff. So there's a whole bunch of options here. So I'm going to show you guys. Yeah, so I'm going to help you guys out. So I'm going to show you one way, which is pretty fancy. We can just do a query. And so we can say banner pos is equal to 0. And you can see here when we do that, we get all those click guys right there. So that's one way we could do it. There's a couple other ways we could do it as well. So we also could have done, I think Hazel kind of was saying square bracket going on. So one way we could do this is we say, okay, the df raw, this is going to be, what's here, banner oops, position, and that's equal to 0, right? So one thing you'll note, and note this will get overwritten, so it's just going to be this part. This is just true, true, false, right? It's just a series. And that's not really what we want. So this right here is what we call a mask. So one way you could write this, and this is usually what you write. I don't really like it as much because it's kind of messy. Basically, it will say, okay, using this data frame right here, basically use this inside part to say if it's true, get that row. If it's false, don't get that row. Skip over it. So you can see here it'll go all the way to 1,000 or 999, right? Because that's from 0. And we go ahead and run this, and you can see now is that it'll skip over the parts. See, for example, you can see some skipping over. There's 79 that's missed over. So that would actually get it. One way I like to write this, and this is all obviously preference, I will write this as its own separate thing. Is I'll call this like a mask, and that's what usually you'll hear it referred to. This is kind of like its true false mask, and I'll just call it mask. Okay. You could also do like mask as 0 or like something more descriptive. So it's a little bit easier to understand what's going on there. So I would do like banner. And you'll notice for my style, I like to like make things very long and long-winded. You'll see a lot of people not like that, but I kind of like it because then it's easier for me to read and stuff like that. So if you don't have it this way, you might put in a comment saying, you know, mask for getting this specific part or getting just this position. Okay, so these are 2 ways you could have done it. I'm sure there's other ways we could have do as well. We won't drag on it too long, but I'm going to keep this one because this one's nice and neat. So you can see here's an alternative. I'll just call this alternative. Just to kind of keep that. I would normally just delete it, but we get our nice thing here. Okay, and then we should also get our experiment, right?
Talk more about the query. So it's like, yeah, cool.
Yeah, so you can start doing, you can actually use like a query string kind of similar to like what you would be doing it for, what's it called, like columns in a frame. So there's some examples and stuff. You can go really deep into this kind of stuff. So like here's an example right here. You can do a query of like A greater than B and stuff like that. And that's equivalent that they showed just saying this thing right here, which is basically it's building a mask and going through. So it's directly going into the columns and using that comparison.
Okay, and then it grabs all the rows where that is true.
Right, that's right. And so this is, I like this one because it's readable. It's pretty, it makes it pretty obvious, like, oh, I'm looking for this specific banner type. So, cool. Right. And yeah, and I'm sure you can probably come up with some fun stuff going through. You usually see this more often, this style. I don't know, it's kind of messy to me. I think we can do better. So let's go ahead and do banner position equals 1, right? So cool. Oh, that's not control. We want experiment, right? So we got experiment. Cool. Ah, that was a lot of work for very little, right? No. So now it's like, okay, cool. We got our experiment. We got our control. Next thing we got to do. Anyone got a guess?
Find the average for each group.
Right. So we got to find the average, and average of what, right? So we have our control. We have this whole, like, we have all these different columns, right? So how would you find that average in this case? Or what column should we be looking at, I should say?
Click, like we're summing click.
Right, all we care about is the clicks, at least for this part. So I was like, okay, well, let's go ahead and do this. Now, the thing is like if we just do, we could do this a few ways. We could explore what the average is first. So we can do control.click, right? And that's just getting the click column. And I can just do just mean, right? Say how many clicks does it have, okay? And you can see here, this is basically, it's going to add up because it's 0 or 1. It's just going to add up 1, 1, 1, 1, 1, 1, right? Going through, and then basically because the average is divided by how many total, which is basically it's like, oh, that's going to be our percentage. So this is going to be the mean directly on here. So just our, essentially is how many of all the different ads or different people on those ads, what percentage of them actually clicked. So what I'm trying to get at is that what we could have done equivalent to get this value, we could have done control.click equals, well, let's do the query again. So we can do this equals 0, or we got 1, sorry. And we could have divided by just the control, what's it? Shoot, I'm missing myself. Let's do click dot count, right? Oops. It's in both. What am I doing wrong? Yeah, okay, I'm gonna ignore this for now. I'm not gonna go through if you guys are okay. But basically you'd find out how many are in here. In this case, there are 1,000 clicks, right? I guess I can do that. What is going on? You guys see what I'm doing wrong? Oh, I see. Okay, this is a string. It's not an integer. I bet that's why. No? Oh, well. It worked the first time, so let's just ignore this part, right? If I was really cared about it, I might go dig deeper and say, oh, what's going exactly on? But we're just going to stick on this. If you guys realize what I did wrong, definitely let me know. But anyway, this will basically just get our average, right? And we can also do the average for the experiment. Oops. And then I also could have done it this way. And you can see here, our average for experiments, 18%. Our average for control is 15%. So that by itself doesn't really tell us much if they're actually different or not. So we'd actually have to make a t-test, right? So this might give us an idea though, at least. So one thing you could do, you could like plot this out, for example. You can say, you know, control click histogram, which is going to be weird because, oops, I got to spell click right. And come on, plot that out for me. There we go. So you can see here, like we can see like, oh, this obviously, if because it's only 0 and 1, we're only gonna get this distribution. But if it was something out of a continuous variable, I could do a histogram and see the distribution of that, you know, what's going on. So we'll actually make a, I'll just keep this in here, but we'll go ahead and make our actual t-test now. So I'm actually going to use SciPy. So I'm actually gonna bring it up here. I like to keep all my imports up here. So import SciPy.stats. Okay. So, or I could also do, yeah, let's do it that way. From SciPy, import stats. And so with that, I can actually use the stats p-test in here. So I can do stats.t, is it t to the next? I'm gonna make sure I have my right guy. Yeah. Oh, it popped up. I didn't see that. So let's see, TT index. Why is it? Did I spell it wrong? Stats.tt index. Okay. It's my oh, I didn't spell test. I was testing you guys. Okay. So now what this is going to do is going to take our distribution A, our distribution B. We're going to do equal variance equals true is the default. Is that what we want? Probably not, right? So remember, we want to do a Welch's t-test. And you can see here in the documentation, if you look at equal variance, if true, it will perform a standard independent t-test, assumes all equal populations. If false, it will perform a Welch's t-test, which is not assume population variance is equal. So note that it doesn't explicitly state sample in variance. When we say Welch's t-test, it just means it's both. So we don't have to worry about the sample size being different. Because by nature, if the sample size is different, the variance should be different too. Okay, so I'm going to go ahead and put in my different parts. So it should be our control dot click, right? Because that's the thing that we actually care about. This is the series itself. And then this is our experiment dot click. Like I said before, I'm just writing it two different ways to show you guys it doesn't matter which direction you go. And then I'm going to do equal variance is equal to false. So it's a t-test, or a Welch's t-test. So I'll say Welch's, Welch's t-test. So, but note this is two-sided. So do we want a two-sided t-test? No, right? So we'll see what our values come out here. So what we'll see actually is t and p, but just to run this, you can see our t index is our our statistic, which is our t-statistic, and our p-value is this guy right here. I realize I'm getting different values from what I had from here. Interesting. Sorry. Oh, I just realized I'm using different number of size. Okay. So I would say, okay, this is t comma p, right? And so now what would happen if I get print t, print p? You can see here's the t-statistic, here's the p-value, right? Note, however, it is going to be a, what's it called? A one-sided, right? Because we want to do that. So we would just divide this by 2. And that it gives us our p-value. So based on this right here, we didn't really say this before, which is kind of bad on us, but just looking at this value, can we reject the null hypothesis? No, it's too big, right? Unless we're really accepting some really weirdness. So I was like, okay, that's not a huge part. So I really should have said up here, like, what is our significance we want? So I know we technically already saw it. What would be our significance, our alpha? Okay, right? So 0.05, right? And we can change that depending on like what our thing is. But this is clearly not going to do very well. So what do you think went wrong? I mean, do we think that there is, like, in this case, like, oh, it's not significant or not? Maybe, right? So probably, right? It's probably not significant. Maybe it doesn't really matter if it's position 0 or 1, right? To double check this, remember we only went for a small value. 1,000's actually pretty big. But just to kind of prove my point is if I go to 100, right? Let's go ahead and just run this whole thing. Okay, and you can see here we have 86 and 80 and 16, right? So about the same proportion, you can see that's going through. But our t-statistic here is 0.02. If we did 100, we might have actually accepted this. So this is where it's really important to understand, you know, like what you're looking at and what's significant or not. Also note that we might not have done this randomly, right? This also could be like subgroups within here. So to really go into, let's just make it bigger, right? Let's do a 5,000, right? And that's not too bad. Let's do a restart and run all. And just FYI, you shouldn't like technically do this, like restart and go through and say, okay, now I'm going to use a larger amount, because then you will only, like, essentially, because what hopefully this makes sense is that if you get like a p-value that's not significant and you're like, oh man, that didn't work, and then you try it again, you're going to bias towards getting a significant value. What I mean by this, and hopefully this kind of makes sense when I say it, is that you only stop when you get a good p-value. But you would never get a p-value, a good p-value, like, oh, cool, significant, and just stop right there. Usually you'd like, I mean, you wouldn't get a good p-value and then continue on and try to keep going until you get non-significant. So be very careful about that issue. I had this thing, this is me, I don't know if I can say this, forget it, I'll say it anyway. When I was working for a school, they would test the students with like a standardized test that they could take as many times as they want, which is awful already. So if you didn't do very well on the first standardized test, they would test them again to see if they actually said, oh, maybe they didn't do very well. And then surprise, surprise, whenever they took the second test, they all tended to do better. And it's not because it was the same test, but it's because the only people who would actually take the test again is that they did worse than expected. So the thing is, if you test them again, you're going to basically regression to the mean. Basically, you're going to eventually have people who's going to succeed more. It drove me crazy because the math person who was leading it did not understand that issue. But anyway, not a big deal. And you can see here when we do a lot of values, we can see 30.31. That makes sense. And that makes sense, hopefully, if we have a large amount of samples, there's less variation. For example, we did only 100. There could have been a lot of variation. And essentially, that is our hypothesis test. This right here, at this point, you can say it's, oh, it's not significant. Banner position doesn't matter, at least when we compare it with these two parts.
But Victor, don't like funky things happen when your sample size is like too big? Like you can find by chance like patterns that aren't really there or something? Yeah,
so this is the tough thing. And that's true for all statistics, right? Is that you can always find things if you just by chance to get there, you might get a big group of this. And this is why it's really important to not just simply when you get an insignificant p-value, just add more to there to see if you get a bit significant. And the reason why is because, and I think that might be kind of what you're alluding to, is if you have, let's say, for example, I'm going to draw on my board. Where is my drawer? Okay. Ooh, ugly green. I don't want that gross green. I want a nice green. Okay. So we have like a distribution of people, right? And let's just say this is the true distribution of what it should be. But instead of us grabbing like, you know, about here, so sometimes we'll grab off to the sides, but for the most part, we'll kind of grab in the middle here, okay? The thing is, we could have technically, the first time we tried it, grabbed right here, right? And so what we might say is like, oh, this wasn't significant. Like, let's say you're like on the edge of significance, like you're like 0.06, right? You're close to 0.05. You're like, well, maybe I just need a couple more people, you know, and get a couple more people. The problem is when you do a couple more people, you could potentially grab over here, over here, over here, which would show you, oh no, you shouldn't be significant. We really were like not significant. But there is a probability that you grab some people over here, and that would pull your sample closer to the edge. For the most part though, if you grab many, many people to begin with, not after you do your test, but if you grab many, many people to begin with, you're more likely to get closer to the middle here because of basically the central limit theorem. That's what kind of the central limit theorem guarantees us, is the sample of samples is going to be closer to the average. Now, speaking to this though, is that if your distribution is not normal, then you might have an issue. For example, if you have like two humps like this in your distribution, these might be actually describing two different groups. Maybe there is another thing, like maybe it's like type of phone is splitting this up into two different groups. In that case, you really should be splitting it up into different types of phones. And this is where multivariable or comparisons would be useful and say, okay, like what things might be factors. Now, note that I said multiple comparisons. Be careful with that, because what I just described here is like, oh, maybe it just depends on what phone they have as well. This could be an interaction. So maybe if you have, I'm gonna make something up. Like let's say you have like an Android phone that doesn't have like a little thumbprint, right? It's at the banner positions right here. And it's like, okay, that means that, you know, people are more likely to click on this because of such reasons. And then you have an iPhone, which has like a different, let's say it has a thumbprint and it has a little banner at the bottom here. Maybe it's like easier for them to realize, oh, I'm not gonna click on this by accident. That's an interaction now. It depends on what kind of phone it is to begin with. And so you have to be careful with that with your model. And this is actually something we'll talk about for next module, extending linear regression, where we'll talk about interactions, where we really haven't, like, if you remember back, you know, way back, turn back time and think about like when we did linear regression. Our linear regression always was something like, you know, y is equal to a1 times x1 plus, you know, a2 x2 plus, you know, let's say a0, some constant, right? The thing is that this is assuming that each x1 and x2 don't interact at all. But you could potentially have something like, you know, the same thing, but then have like a third factor where it's like x1 times x2. And that basically means that they're interacting between there. It's no longer linear. This is kind of like the situations I'm describing here. And that's why, like, when I talked about ANOVA, however you want to pronounce it, it kind of matters in the sense of, if you're doing multiple comparisons, you have to consider that you might be having interactions and what is your model actually saying? And this can, where ANOVA can get very, very complicated and say like, oh, what are you gonna do? Usually it's best to do like, I mean, in practice, I think, this is my opinion, is you basically do ANOVA to do an F test to say, is there a significant difference between these multiple groups? And then once you have that multiple significance, then you might compare those parts. And there's other ways you can check if there's interactions and stuff like this, but that's not something we actually talked about. So again, you can go pretty deep into statistics for quite some time. But for the most part, going back originally like to Tara, like your original thing, for the most part, grabbing more people to begin with, not as a result because you think it's significant, it's usually a good thing. There's very rare cases other than maybe the data set is not shuffled. So in this case, you might want to actually shuffle the data just to make sure there's not any weird bias in just the structure of the data itself. Does that make sense?
Yeah, it does. Thanks.
Okay, cool, no problem. All right, so yeah, this is really A/B testing. Like this is, like I said, it's not too bad. One thing we didn't really show is if you did the opposite, where you are designing the program or designing the test, and before you even grab, you know, say before you test out different banner positions, you might say how many people should be tested on. That's when you would actually use power calculation. And this is, for example, I don't believe SciPy actually has it built in to their package. So it'd be either one, you design it yourself, which is like, oh, that's no fun. Or two, you probably use another package like stats models. Stats models is a more robust, more mature statistical package. If you were a statistician and you were really big in stats, you probably would be using R. So this is why, for example, you'll see stats models, OLS, use R notation essentially, because all the people who were statisticians who came from R and moved into Python were like, hey, we should make something that we're used to. And that's what they designed. So just kind of be aware of that difference. Okay, cool. Yeah, so hopefully this doesn't seem too intimidating, right? Going through here. Like if you look at everything I did, other than importing it, essentially I just said which one's the control, which one's the experiment. I chose which column it is, in this case, the click column, right? Okay, and I said, okay, those are my different parts. And you can see here, oh, this makes sense with the larger values. They're very, very similar to each other. But we do this histogram, or not histogram, we do our t-test right here, and we can say if it's significant or not. Okay, one last thing I should say too. If we did find significance between the two, what could we say it mattered, if that makes sense? Like what could we say if it was significant? Should we suggest everyone say, oh, we should definitely put it at position 1 as your main part because it has a higher click-through rate? I see Barta going, maybe not.
Well, it's what same thing we discussed the other day, right? So it may be other factors affecting those, you know, users clicking on the banner, like, for example, like they realize it's something new, so maybe it's you have to wait for some time until users get used to it and things like that, right?
Yeah, so we have to consider there might be some conflicting variables and stuff like that. Like we have to say like, hey, once you have the result, you have to say, does this make sense? And if it does make sense, or like, can we get a reason from it? The statistic itself just says it's significant. It doesn't say why it's significant, right? So we always have to be aware of that. And that could be a good thing. Like it could mean that it doesn't matter what we do. It's like, well, if we do this, there might be other factors, but those other factors kind of add up together and they end up getting this result. There's another subtle part in here. So let's say I do get like these values, 17.8% and 17.1%. And we did find they were significant. So that maybe their variance was very, very small. What would you suggest to the business if it was these results and they were significant or low p-value? Would it make sense for them to make a change? Maybe, maybe not, right? So a 0.7% increase in click-through rate, right, from 0.7 like absolute, might not be enough for them to really warrant to redesign some stuff. If it's a really simple thing, they'd say, cool, it moves the needle up, let's make that change. But if it, let's say, took like, they had to go hire a whole team of people and they had to go do these other things and it's going to cost like an extra $100,000 just to implement this one feature to get a 0.7% increase, then even though it's significant, the effect is so small, it might not be worth them doing. And this is where it's always important to know, not just what the click rate, like this is the click-through, TTR, right? The click-through rate. It's also important to understand, well, what does that mean to the business? Does that mean a significant value to it? And that's, in the end of the day, it's all about revenue, and for businesses at least. I mean, you can say there's other things, but basically it's some value, whatever is the value, and usually that's revenue. Okay, cool. All right, I know I kind of went on a little bit, but hopefully you guys have a better picture of what A/B testing kind of looks like. Hopefully you're also not as intimidated by it. I think sometimes it sounds very intimidating. But for the most part, you're essentially just doing a t-test against different groups. Okay, and then going to multiple comparison, the only difference between multiple comparison and then into like for A/B testing is that you're basically just doing many different comparisons. If you use stats models that we show in the curriculum with ANOVA, you'll see that there's a printout for each individual like comparison. Those are just basically all different tests and getting different p-values, basically comparing like different groups together. Obviously, you don't want to do that by hand because that would take a long time. So that's why we have packages and stuff like that. Cool. All right. Any last questions before I let you guys go? It's Friday, everyone. should have a great evening tonight. Cool. All right, so I'll go ahead and stop recording then.